Back again. So one of the most important products then of Schrodinger's wave equations were this set of quantum numbers that can be assigned to each electron in an atom. They represent, if you will, an address that describes completely the electrons in any atom. Each electron is identified by 4 of these quantum numbers. Unfortunately, these quantum numbers have complicated names that are not especially, at least to us, representative of what they portray, but we'll try and wander our way through this and simplify it considerably. Not surprisingly, these quantum numbers have abbreviations, right, that we'll talk a little bit about, and as you can see, some weird names, but nevertheless, they are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number that uniquely identify these different properties of the electron. So let's sort of take them one at a time. We'll sort of see at the end how we can make an association between this and the periodic table, which is very helpful to us. Principal quantum number then corresponds to the energy level of the electron, perhaps the most easily grasped concept. And indeed, these energy levels are the same as the periods of the periodic table. Isn't that cool? That is to say, those rows of the periodic table correspond to these various energy levels in general. Note that if you view a periodic table, there are only 7 rows to it, and this represents then the 7 energy levels that are occupied by ground state electrons. We can send electrons to higher energy levels, again by energizing that atom, but when we remove that source of energy, all the electrons return to and live comfortably in the first 7 energy levels in this ground state. Note that then the n can take on any positive integer in concept, but of course we routinely only deal with 1, 2, 3, 4, 5, 6, or 7, those being the ground state condition. The angular momentum quantum number is awkwardly named, but what it really is a shape for these electron spaces, and we're going to see in just a second that these shapes are rather distinctive. Sublevel is another way of thinking about it. We use the term orbital now as the general term to describe the space that the electrons are occupied. And note that the number of possible values for the angular momentum quantum number is equal to the principal quantum number. Now that's kind of a weird thing to say, but if you think about it, it goes like this. If your principal quantum number is 1, right, then this shape variable can only take on 1 value, and we assign it a number of 0. More on that later. If the principal quantum number is 2, then we can have a angular momentum quantum number that can take on any one of 2 values, and we call it 1, and away we go. These were historically given letter designations, and here's where the story gets a little ugly in the sense that we now have 2 different ways of referring to these things. But we'll see these in lots of textbooks, and we'll talk about them, and this is a nice point of connection to the periodic table. So the S, P, D, and F orbitals then can be identified as blocks on the periodic table. We'll see that in a little bit. And they have then angular momentum quantum numbers of 0, 1, 2, 3. Indeed, there are higher levels, but they are not occupied by ground state electrons, so we don't worry too much about it. In fact, as we've said before, we rarely go down into the rare earth element rows, and so to a large extent the F orbitals are not of special significance to us, but nevertheless, there you have it. Here is a diagram that I found out there that you can find out there, I'm sure, that attempts to show you then the angular momentum consequences of the different letter designations, the shape. And so one thing you should take away from this is that the orbitals, S, P, D, and F, have different shapes, and as we go to increasingly high letters, the shapes get increasingly outrageous in terms of their configuration. These are, in fact, the solutions to Schrodinger's wave equations, and as you can see then the derivation, the waves represented then by these various forms of orbitals. So here then an S orbital is spherical, a p orbital is sometimes referred to as a dumbbell. D orbitals sometimes referred to as double dumbbells, although you can see this one here is a little odd. And likewise, F orbitals, increasingly complicated in their configuration. So this would have an angular momentum quantum number of 0. All of these would have an angular momentum quantum number of 1. All of these would have angular momentum quantum number of 2. And all of these would have the angular momentum quantum number of 3. If you look closely at that previous diagram, and I'm going to show it to you again, you'll see that the electron spaces can take on different orientations in most of those different shapes. And so we have a third quantum number, weirdly called the magnetic quantum number, that captures this variable. And in fact, as we'll see in just a minute, the number of possible shapes, right, depends on the value for the angular momentum quantum number. For example, if your angular momentum quantum number is 0, you have an s orbital, and since an s orbital is spherical, there's no different way you can orient that to define a new space, so that the magnetic quantum number, which is best thought of as a orientation number, has to be 0 also, because of the lack of any different orientations that exist. If, on the other hand, your angular momentum quantum number is 1, defining a p orbital, there are actually 3 different orientations, x, y, and z, that are possible. And so there are 3 different magnetic quantum numbers that can be associated with this. We, by tradition, number them from negative to positive through 0, so that the 3 possible values are -1, 0, and 1. Again, if we use these as the representations, this then would have a -1 magnetic quantum number. This would have a magnetic quantum number of 0, and this would have a magnetic quantum number of 1. All of those then possible values for angular momentum quantum number of 1. Notice how this then sort of expands as we go up. If our angular momentum quantum number is 2, which corresponds to a d orbital, we now have 5 possible orientations shown here. These actually have more complicated names, but we'll just represent them as they do here with the magnetic quantum number of -2, -1, 0, 1, and 2, using our same tradition. And indeed, if we move on all the way up for L equal to 3, giving us F orbitals, note that we now have 7 different orientations, numbered traditionally as are the other ones. And if we go back here, we can see those 7 orientations and the value for the magnetic quantum number, -3 through 0 to +3, giving us those possibilities for electron locations. Obviously, we can go higher, but we remembered that there is no electrons in orbitals at the G level. They would not be in the ground state, and so we're not going to worry about them. Just threw this in again in case I needed to refer to it again. The final thing is the spin quantum number, which can take on one of 2 values. And by tradition, we have a -1/2 and +1/2. And 2 electrons are allowed within each orbital defined by the magnetic quantum number, and they must have opposite spins, likened here to magnetic poles. Here, of course, the representation is of electrons as particles spinning in different directions, but we'll see that all that does is give us a way of addressing the 2 electrons, whatever they might be, that are occupying each one of those sublevels. We'll pick it up there in the next video.